already with us. So let's start with today's webinar. So I'm Flavia Tomarchio. I'm Head of Innovation at Deployment at Constructor, and I'm going to be your host and moderator for today. Let me quickly go through the agenda for the webinar. I'm going to guide you through a little bit of an introduction of the Constructor ecosystem, and then we will dive in with our main keynote speaker, Professor Costantino Vosello, that will talk about this new advancement in material design and talk about functionally intelligent materials. And then we will have a demo of the Constructor research platform from Nikita Kazeyev. At the end, we will go through the Q&A. We have already some questions you have been submitted, and we will also reply live. So please put down your question on the chat, and we will make sure that all is answered. So just a few words about the Constructor ecosystem. We have a Constructor ecosystem is definitely global and local. We are physical, virtual, and our main legs, let's say, are some non-for-profit entity and some for-profit. We have Constructor Knowledge, underneath which we have Constructor University campus in Bremen. It's a fully fledged university that spans from physical science, natural science, business, social sciences, and is quite a unique place in Germany. Constructor Institute in Schaffhausen, that is more focused on computer science and software engineering, and Constructor Learning, that is executive education. Then we have Constructor Capital, that is a venture fund that invests in different type of technology, edutech, AI and ML, physics, of course, quantum. And today's focus, that is Constructor Tech, that consists in research platform for education and learning. Talking a little bit more into the Constructor technology infrastructure, the platform is an end-to-end system that has different type of infrastructure. The platform that is dedicated for learning and teaching with new technology in terms of adaptive learning, constructive learning, and hybrid. So all the new technology that are developing these days in the learning and teaching scenario. A lot is done with the platform also in the, let's say, more administrative part of education and science, like finance, CRM, and similar infrastructure. And last but not least, our focus of today, the science and research platform. So computational research, simulation, modeling, and we will know a little bit more later on with our talks. The platform addresses the needs of a different type of audience. We go through, let's say, a little bit more on a admin level, like VP of research, IT directors, dean at the dean level, but also, of course, the focus is on the academic side with tailored options for professor, for postdoc, but of course, as well as the students that can use it for collaborating on their research project, running experiment, and work on their results and analysis. We know that there are a lot of tools, of course, on the market, more than 300 applications that combine different projects in terms of hardware, software, infrastructure, etc. But sometimes it's very difficult to navigate through all of them. So it's definitely important to have the possibility of clustering in one single panel all this infrastructure. And this is what the research platform is actually about. We can have a user interface that works with different type of experiments and also different type of needs, like from the head of the lab, the experimental researcher itself, more on the computational side. And this platform, let's say, couples all the different type of tools in one panel instead of having to go through the different ones at the time. So this was a little bit about Constructor ecosystem, and now let's dive in our main part of the seminar. So let me introduce you our keynote speaker, Professor Costantino Vosello. Is the director of the Institute for Functionally Intelligent Materials at the National University of Singapore. He is a Nobel laureate for physics, well known for the discovery of graphene back in 2004. And now today is gonna talk a little bit more on a new adventure of these new materials that are functionally intelligent materials and how this will couple also with advancement in technology in AI, machine learning, etc. So now I leave the floor for Professor Costantino Vosello. I leave the word to you, and I'm stop sharing.
Great.
All right.
Thank you so much for your kind introduction. It's really a great pleasure to be here. I hope you can see my screen now. Yes, and yeah, so we've been collaborating with Constructor Tech for a number of years now, and I'll try to present a few projects, a few results which we achieved together. But the convenient starting point here is still, well, surprise, surprise, is graphene, because it's of course is the first two-dimensional material. It's only one atom thick, only carbon atom, so it's very, very simple material, you can think, but at the same time it has a number of those superlatives which, well, it's the most conductive, most thermally conductive, flexible, impermeable, stretchable, and so on and so on and so on, and all those all those superlatives suggest that it can be used for a variety of very different applications, from sensors and energy to composites and optoelectronics. And of course, when it comes to its properties, especially electronic properties, it's everyone would agree that it's very, very special material. Is the first material with the linear dispersion relation for electrons, where electrons mimic massless relativistic particles. But when it comes into applications, it's actually not that special at all. It follows exactly the footsteps of many other advanced materials before it, like carbon fibers, carbon nanotubes, fullerenes. They start to be used first in sport goods, because you can, in composite materials, because there you can charge premium for minute improvements of the properties. So we ourselves are guilty. We collaborated with Richard Miller and McLaren to make this world lightest but also world most expensive watch. But then step by step, it started to get into a variety of different applications beyond the composites. In thermal management, it's really probably the most important material in thermal management. It's a very serious problem for modern electronics. You need to dissipate a lot of heat from ever high density integrated circuits, and graphene is the unique material in this respect. It has the thermal conductivity higher than like 4 times higher than copper, and it is flexible at the same time. So it's one of the key components for the new affordable phones. But if we need to look forward, for example, I would say that probably applications in such areas as the optoelectronics, because most of our internet traffic goes via the optical fiber, of course. But at the same time, we don't have means how to control the signal and modulate the signal in the optical domain. So every time we want to do something with the signal, we have to convert it back into electronic signal, and then do something, then convert it back into optics. Ideally, you don't want this. You want really everything to do some signal processing in the optical domains, and for that we use the silicon photonic chips. But in order to make them active, you need some materials where the refractive index can be controlled with the external gate voltage, and that's all graphene. Now, of course, there was a question if we can produce enough graphene, because a long time ago we started with the very simplistic way of making graphene by Scotch tape. You take a piece of graphite. Graphite is the material which you find in your lead pencils, and then you exfoliate it and you get graphene. Now, what we can do, we can produce graphene by other means as well by chemical vapor deposition. So that's the way how you produce graphene for electronic industry. So is the electronic grade graphene, or by liquid phase exfoliation. That's you make it for batteries, for coating, for composites, as well as many other ways how to make it, like so many different epitaxial techniques as well. But the next step in the story happens when you start thinking that maybe if you can take other pencils, not only the lead pencils, you can make other materials, not only graphene. And that's indeed the case, and that's indeed the way how other two-dimensional materials have been produced. And all of those materials, they have one thing in common: they are only one atom thick, or one unit cell thick. But at the same time, they have really a variety of different properties. So some of them are insulating, some of them are very good metals, semi-metals, semiconductors. There are ferromagnets, there are ferroelectrics, there are superconductors, you name it. So now we are really talking about a full family of two-dimensional crystals. It's not only graphene; it's really a huge family. I would say probably experimentally, probably good couple of hundred of those materials have been investigated. Theoretically, many thousands have been predicted. So we have really quite a choice now when we want to study two-dimensional crystals and some physical phenomena which are sitting there. And of course, the physics in two dimensions can be quite different, quite advanced in comparison with the physics in three dimensions. But then there is also another opportunity which are given to us by these one atom thick materials. Because now, if you imagine you come to your lab and you have those layers of materials in front of you, well, what you can do, you can start combining those individual layers into stacks, into three-dimensional stacks, but in the way the nature never intended it to be. And then you create this artificial material which has the where you can tune the properties according to your needs. Now this is really, it's quite a powerful technique, and lots of groups in the world do play with it, and a lot of new phenomena and new devices have been demonstrated, like tunneling transistors, resonant tunneling diodes. So here what you see is light is a light emitting diode. So you basically, so graphene plays here only a secondary role. So it's a transparent electrode, but at the same, so you just inject electron hole pairs and they recombine in those quantum wells, which are those blue atoms. And so it's typically some layers like MOS2, tungsten sulfide, tungsten selenide, transition metal dichalcogenides are being used, and then you can extract light from such a device. So it's been so quite a variety of different heterostructures have been created. And just to finish this introductory chapter, introductory part, just wanted to say that because there are so many of those two-dimensional crystals, so we can create quite a variety of different heterostructures. But now we can control not only which crystals and how many layers do we stack together, but we also can control how do we do it. Because if you start rotating those crystals, even a tiniest angle of rotation would change the crystal structure, sorry, the electronic properties of those materials. So I hope you can see on your screen there is from time to time this mesmerizing periodic pattern appears. Is the so-called Moore pattern, and apparently it controls the low energy properties of electronic properties of in those materials, and you can really vary it with tiny changes of the angle. You can vary it significantly. Thus, MIT group has demonstrated that by simple rotation of those crystals by about 1 degree, you can turn it into a superconductor, or you can turn it into a mode insulator, or in slightly more complex heterostructures, you can turn it even into a ferromagnet. So you really get quite a variety of properties and very good control over the properties of those materials. And this basically opens us a very nice opportunities, because now we are not really limited by the materials which are given to us by Mother Nature, but instead we can produce materials on demand, materials with the predetermined properties, simply by stacking together atomically precise layers of different materials. But that, of course, brings a lot of challenges as well, because you immediately need to, if you want to model the properties of those and layers, many different atoms, and the traditional ways how to do it. So usually people use the so-called density functional theory, which is a very powerful technique, but it only capable to work with a small number of atoms, few hundred, maybe 1,000. If you want to do something, a structure which is bigger, and you really need to deal with, ideally, with tens of thousands atoms, maybe even more. In our cases, you're really stuck, and that's why one of the applications of the machine learning was to try to speed up the computational processes for such a complex devices. So we are not alone here. So we collaborated with SEER to develop this new methodology, new approach in density functional theory. So it's quite different from the traditional Kohn-Sham equation. So we call it D4FT because it's deep learning, but it is also differentiable direct optimization. So for the DFT, and you don't solve the Kohn-Sham equation. So you try to optimize the density functional by itself, but at the same time, and then you solve the problems of the optimization separately through the machine learning processes. And indeed, so such approach has been shown to work. It has been shown that it scales as n cube rather than n4, and to the power of 4 it was the number of atoms, but and it converges much faster, especially for the large system. So we are planning to produce a package based on this, but at the present time, we're still testing it for different systems to be sure. But if you are interested in using this package, you're more than welcome to collaborate with us. Please contact me after the talk. Another direction of research which became quite possible is the try to control the properties of the atoms, not only of the materials, not only on the layer scale, but also on the individual atomic scale. Just to give you one example, some time ago, people realized that you can get single photon emitters, basically quantum dots, which emit only one photon at a time by utilizing defects in the two-dimensional material. So this work started with quantum dots in tungsten selenide, and then now probably the most popular material is hexagonal boron nitride. And it's quite important. It's quite important work because single photon emitters are extremely important for quantum telecommunication. For example, so if we can design those quantum dots in our materials and we can control their properties, so we can produce quite complex quantum devices. So as I said, boron nitride is probably one of the most promising for in this case because it has a huge band gap, and we do know that in order to produce single photon emitters there, we have to dope it with carbon. The problem is so that, okay, we know that it works, and we know we can see in the optical spectra those sharp lines which are associated with the single photon emitters. The problem is that we still don't know what emits, what kind of defects, what kind of quantum dots emit in those crystals, and what can be and which if we don't know what emits, it means that we cannot design them further, and we cannot introduce the rational design. So to this end, I mean, we can even see them in the STM measurements. So what you see now on the screen is the STM measurements. We see that there are individual defects, but it's very, very difficult to figure out what's the structure of this defect. You really have to guess which defects are the most stable upon doping with carbon. So it can be single carbon substitution, or a combination with a vacancy, or a combination with another substitution, or with two vacancies, and so on and so on and so on. And in order to do that, to figure out what is the property of those of those defects, but also maybe to assist people in rational design of those defects, we created a database of all the possible defects in the not all the possible, but of the reasonable number. So you just all the possible triple defects in 8x8 unit cell to be precise. But of course but we tested many more defects in a variety of different two-dimensional crystals. And the task is that if we can have this database and we we train our machine learning approach on this database, we can probably explain the properties of the more complex defects as well. It turned out to be that we have to put some quantum, we have to teach the neural network to some quantum information. So we introduce some additional ways how to set up the descriptors for those defects. But at the end of the day, if you do it, it does work quite well. And this work is now published as a database. It is open, so people can use it. And I think at this moment it's probably a good time to ask my colleague Nikita Kaziev to give a little bit of an introduction to this database and what can be done, what can be done with it. Nikita, please join me here.
Okay, thank you for introduction, Professor. Give me a second to start sharing. and I will show how this research looks on the Constructor research platform. Okay. So our journey begins with the paper, and now it's a very good paper. So I'm sure that after endorsement by Professor, you're definitely going to read this paper and arrive at the code availability section, where it is. And want to reproduce results and use our models. Yep, here it is. So you click here, we go straight to the research platform. This is the landing page. We have here is the abstract. And we have the publications, which are converted Jupyter notebooks. So this particular one contains the processing of the latest results computed on the platform. And we publish the data set as a database as tables, where you can see the structures, the sparse representation we propose in our article, and scalar variables which you used. Now, in order to get access to the model weight of the code, click duplicate button, which I'm not going to do because I have quite a few copies of this project already. So what I would do is switch to the tab. This is how the project looks like. Or it traditionally opens with a README file, which describes all the necessary steps to reproduce the results and train the models. So the paper proceeds in a traditional fashion, where we extract the necessary information from vast data, evaluate the different set of machine learning models. All the computations happen inside workflows, which are the way to use the Constructor research platform for heavy computations. This particular node is not so heavy though, it's just data pre-processing. This is the script, which we call, and here we request the resources. As you can see, we are not asking for that many resources because it's a cheap node. Now, so the rest of the workflows, they run additional pre-processing steps. And finally, we evaluate baseline models, and we evaluate our own model, which we propose in the paper. Finally, we train our model on the whole data set, both train and testing parts. So you could use it for making predictions. Now, this is how it looks like. Okay, it's a notebook. Don't be afraid by the amount of code. Most of it is used to generate interface, which I will show you in a moment. Okay, here we go. Loading. Now we have two options. The one which we will use now is the graphical interface, which would allow us to generate some random structures with the defects. I will go with OS2. We'll have a large number of vacancies in it. You can see that, okay, let's add some molybdenum. And so we have the pristine structure and an example structure with the requested number of defects. We'll proceed with the data generation. Okay, we're not going to upload anything right now, but it's obviously an option. So now we have generated our 100 structures, and we'll select 5 of them and take a look. Yes, that's what we expect to see. Carrying on, we will compute the sparse representations where only defects are present. So this is how we achieve the increase in quality and performance for models. And now we're running predictions. Notice how quick it is. And we're going to analyze the predictions. So start with histograms of predicted values for energy and the Homa-Luma gap. Well, we'll check whether there is a correlation. No, there isn't, and honestly never have been. And we'll do more sophisticated analysis where we will look at the structures across the spectrum of predicted values. So we have structures which are arranged according to information energy per site. And we have structures arranged according to the Homa-Luma gap. So one on the left is almost a conductor, and one on the right has a band gap. And finally, we're going to upload our structures and predictions to the Constructor research platform. Here we go, data catalog, and scroll down. Oh, yes, and this is what we have just predicted. So we have these structures, see sparse representation, and we see the predicted values. So thank you for watching our demo. I'm looking forward to your questions. And I return the floor to Professor Novoselov.
Nikita, thank you so much. So that's indeed. So what you can see here is the other results of such predictions, and the descriptors which Nikita partly told you about really allow us to obtain much better results, better predictions than at least in terms of some of the parameters like formation energy or the position of Homa-Luma energy levels, much better than any other descriptors. Now, the single photon emitters is only one of the possible applications. Why do we want to know the properties of those single atoms or multiple atoms defect? Another very popular topic is the single atom catalysis. So it has been demonstrated in many materials that adding individual atoms would change their catalytic properties quite significantly. And indeed, we played with experimentally with two-dimensional materials as well, which already being used for catalysis purposes. For example, MOS2, quite widely used in petrochemical industry. And you start adding individual defect there, and you indeed can see that you get some improved catalytic properties. So probably the easiest way is to look at this central top graph, and you see that if you start with pure, so zero concentration of tungsten means pure MOS2, you add a little bit of tungsten inside and your Tafel slope goes down quite significantly. Same if you add some selenium instead of sulfur. So it looks like it's a very good area for the application of our database. But if you start simply use it directly, it's not going to work. And the reason is that when you grow, when you produce those materials, they start to experience some, and you start to produce some defects in those materials. They don't only produce defects, but they change their phase structure. Like MOS2, very simple material, but it can exist in a variety of different phases. Means the relative position of those of molybdenum and sulfur, and you start adding individual defects, and suddenly there is a phase transition, and you get into a completely new crystal with new properties. And this idea that you can control the properties of materials by changing their phases and by controlling the phase transitions really brought us to our next topic of our research. What we are mainly doing now in Singapore is the functional intelligent materials. I think it's the easiest way to introduce it, those functional materials to you, is just reminding you those frames from the Terminator 2 movie, and just for you to remind you, Terminator 2 was made in 1991, and for those who didn't watch it, the plot is that a robot from 2029 is sent back to 1991 to kill Sarah Connor and her son. And the only reason I'm showing it to you is to show how people back in 91 thought about future materials. So they thought that in the future, everything is going to be made from liquid metal, self-healing, changing shape, adaptable, changing color, and so on and so on and so on. So now we are in 2023, because we've got 6 years to go, but unfortunately we're not even near fulfilling the dreams of the Terminator 2 movies. And the problem is not only about robotics, right? It's the problem is fundamentally that our technology is very much very much top down. It means that individual components are not functional at all. So the individual components, you really need to assemble them into a system level to gain some functionality out of it. If you take one cogwheel out of this clock, it stops working. If you take one transistor out of maybe a few transistors out of the integrated circuit, it will stop working. So you really, and this top-down functionality is the key for our technology. We're trying to control every single movement, everything our devices produce. At the same time, biological systems, they work on a very different, in a very different manner, and they basically, the functionality is spread across many different levels. Like proteins are functional in their own rights, the membranes of the cells, the organs, and so on. So that's what we would like to do with our functional intelligent materials. We would like to be able to delegate some of the functionalities onto the material level, that materials are functional in their own rights. And so, as I said, we introduced this concept of functional intelligent materials. Functional means that they can be programmed to do certain response to external stimuli, and intelligence, well, we use the most simplistic way to introduce intelligence, which is, as long as materials have memory, that's good enough for us. And let me just give you one example of what I mean. So graphene. So one of the biggest application of graphene is through graphene membranes for water desalination. In some countries, like in Singapore, 99% of our water comes through a membrane, through the desalination. Not graphene membranes, but there are companies in Australia, for example, who do produce graphene membranes. But in this case, it's just, but it doesn't really matter. So whichever membrane you use, you still have to control the quality of water. You put a sensor downstream which controls which sends a signal to the computer, and the computer analyzes it and then sends a signal to an actuator to open or close the water stream. But imagine that you manage to create a little bit more elaborative structure of your membrane, which has some sensing part in it, so which can be triggered by the presence of the toxic species, and then it changes the conformation and then closes those membrane spores. And and in this case, you can imagine that you can think that the membrane has all those functions of a sensor, of a computer, of an actuator inside of its material structure. And that's what we call the functional intelligent materials when we delegated those functions to the material level. So the problem is that, of course, there are no recipes how to produce it. We developed our own, let's say, mnemonic rules that we try to create composite materials with strong interaction between the components. Also, this interaction should go through different channels, like Coulomb, like strain, like van der Waals, maybe hydrogen bonds, and then you should be able to create so-called degenerate energy landscape where you have multiple metastable states close by, and then you should be able to get to drive your system with external stimuli through this maze of the metastable states, and then try to get some useful work out of it. So the idea is not very new. It's exactly how your proteins work in your body. They're so versatile exactly because they can exist in a variety of different different states, and they can be folded. They can be conformed into different shapes and produce different functions, catalyze different reactions. So we are not copying proteins, but we are trying just to copy the ideology that we have a variety of metastable states, and then we can set our materials into one of those states, do some useful function, and then convert it back into the ground state. So as I said, the problem is that there are no real recipes how to do it, because most of our physical formalism doesn't like dealing with the metastable states, doesn't like dealing with the out of equilibrium phenomena, with the phase changing phenomena. So we increasingly use the dynamic machine learning, and we're trying to use the material robotics to produce those data for this machine learning. So when we say machine learning, so usually that's what people immediately imagine. So that's well, this is our collaborators simply filmed our students and then replicated their behavior, their work with the robots. In reality, it's a bit clumsy and very, very difficult to program. So most of our materials, of our robotic devices are very dedicated to produce one kind of materials only, and then you can really, but then you can gain through high throughput of data, and which you can use to train your machine learning models. And let me just show you one example of such dynamic machine learning, and this is the work of Chinchao Li and Keda, who try to learn the stretching and folding of not a DNA but a polymer chain. And polymer chains are significantly simpler than DNAs because they're not charged, so there is only nearest neighbor interaction, but still they exhibit quite a variety of behaviors. You notice that some of those chains are very, very fast in unfolding, and some takes much longer time. And even if you do the simulation and you use exactly the same starting condition, because of the finite temperature, Brownian motion, you actually get into very different behaviors. So sometimes some of those configurations always unfold very fast, some always unfold very slowly, and sometimes unfold fast, sometimes unfold slowly. And we try to create, through the efforts, it's mainly of Chinchao Li, to create the dynamic machine learning model, how to of this dynamic and stochastic system. And in a sense, we are trying to create custom thermodynamics. So let me try to explain you what do I mean. So imagine we take a very complex system like gas molecules in your room. So the full description of such a system is by stating the coordinates and the velocities of all the molecules at a given time. So then you can solve all the dynamic equations. There will be billions of them, but it's still potentially doable. However, practically no one likes to do this. Practically, you rely on the thermodynamic approach. We means human beings, somehow figure it out that you need only some macroscopic descriptors of this system, and we choose pressure and temperature. And if pressure is more or less obvious, temperature is not obvious at all, but we chose them and we figure it out that they're linked together through the equation of state. And so now it's much easier to describe such a complex system. The problem is, it took us quite a number of years to figure out this very simple equation, and it took us quite a number of years to figure out the meaning of temperature, for example, because the Celsius scale is 1740. The proper theory for the temperature is Max Planck in 1920s. So it took us really a long time to figure out this equation and the meaning of the parameters. So the question now is, if we show a machine a complex system like a polymer chain, can it spit out the right parameters like temperature or pressure or whichever parameters it can think for this polymer chain, and the equation of state for those parameters? And then we can find, if we get the equation of state, we can find the phase transitions, we can find the metastable states, and so on and so on and so on. And that's exactly what has been done in this work. It's actually been accepted just a few days ago in Nature Computational Systems, and we just try to, so we model it with the neural network, but we give some structure to this neural network so it knows something about physics. So in particular, it knows about the Onsaga principle, that it should go into the equilibrium with the speed proportional to the potential, to the gradient of the potential, but that's about it. And then we ask it to produce the coordinates, like the parameters like volume, temperature, or pressure, or something, and write the equation of state. Of course, it does it. The problem is those parameters which it spits out. You really need to figure out what does it mean. Luckily, this system, this machine learning system is differentiable, and we can, by differentiating it, we can look at the state of this polymer chain, and we can figure out the meaning, the physical meaning of those parameters with which machine comes out. And if you do everything right, you can really mimic the behavior really well, of course, only stochastically. And then you can write the equation of state, which is basically effectively the potential of and it's the neural network is your potential now, and then you can figure out the different types of the states. Some of them are metastable. There are saddle points in this potential, and so on and so on. So now what we're trying to do is to apply this dynamic machine learning to more complex systems. So I just give you a few examples before we finish. So here is the example of a high entropy alloy which has the self-healing property. So the little dots there are individual atoms, and then in the middle there was a hole, and now it started to shrink because the material was programmed to self-heal any defects. Works much faster on the simulation, but believe me, it works in the experiment as well. Very complex system, very difficult to compute its properties. We hope that machine learning can help. So smart drug delivery, we can produce those capsules which are closed in your stomach but open up only in the bloodstream. Again, it works experimentally, but how to model this dynamic behavior, this phase transition, is a very difficult task. We hope that AI can help us. I mean, we are not limited only for the drug delivery. We can produce lots of those structures, also macroscopic. It does work, but again, it's extremely difficult to model, and we hope that it can be used for so that machine learning can help us here. So I think I will stop here. Just there are lots of applications of those dynamic materials in the anti-corrosion, for example. Similar story as the drug delivery. And I really think that in the future, those functional intelligent material will become more and more important for us. But currently we don't have any approaches how to work with them, and we really hope that machine learning, dynamic machine learning, can help significantly here. Thank you so much. Thank you.
Thank you so much, Professor Novoselo, for this very interesting overview, very much past and future connected together. So now we can move to, we have a few questions already sent out. And I would start with this one for you, Professor Novoselo. So you mentioned that, of course, intelligence at this stage you're mimicking with the memory of a material. So what do you think would be, let's say, all the different type of possible intelligence systems that this material can possess, and the mechanism that you're already foreseeing behind, so beyond the memory, like more in the future?
Right. So we started with the very simple definition of intelligence of materials possessing memories, and then once you have those, you can build quite complex systems. So using memoristas, you can build neuromorphic computers, for example. But then you can actually ask a little bit more. You can ask those memory and those switching phase transition happening with a certain distribution which you can control, and then you can create even more complex devices. So rather than only memory, you ask for some very specific autonomous dynamic dynamic properties, which is again possible. You just use the KT, you use temperature as the energy source, and which can drive the system, or completely out of equilibrium systems, like in biology we have the signals passing through the nerves, or your heart oscillating all the time. Potentially it should be possible to create such out of equilibrium materials as well. I won't even know what kind of applications you can use it for, artificial life maybe, but I think it will be very, very interesting and very rich applications.
Thank you. And now a question for Nikita. So thank you so much for showing us how the actual platform works. And we have a question in terms of, let's say, limitations. So there are any limitation at this stage of what you can model and simulate? For example, there was a question on specific gas material interaction, how complex one, just to have an idea of how functional at the moment the system could be.
Well, there are two questions. So the platform, it's a computational platform. It allows you to run whichever model, algorithm, software you choose. So as a limitation, for gas and surface interaction, it's fortunately not my area of expertise. But naively, I would say that molecular dynamics is the way to go. And you would be limited primarily with time and spatial constraints. Like you cannot model one square centimeter for 1 second, and you can easily model 1 nanometer for 1 picosecond, and everything in between is a trade-off between computing power, time, and accuracy.
Okay, great. So one last question to close for you, Professor Novoselov, just a little bit on a vision. So we see now also on the screen a lot of different, let's say, possible application of these materials. In terms of a timeline, and what do you think would be like the one that more close than the 2029 you showed with the Terminator would be actually easier to grasp, even to really see?
I think it should be a trade-off between the available data and the experimental data, as well as the computational data, and the needs and necessity from the society. And personally, I think the area of batteries and fuel cells, hydrogen fuel cells, or whichever other fuel cells, is a good example, because we accumulated quite a number of data, especially those big companies which produce batteries. They really have tons of data which we hopefully can use for modeling such complex processes as lithium intercalation, lithium charging, discharging, oxidation, and reduction, and so same materials for water splitting, electrolysis, and for fuel cells. So I think those areas, so these areas, they're first of all very important for technology. They still have lots of room to grow, and at the same time, we already now have lots of data for those. So I think we will probably see the first applications of AI and machine learning in those areas, and we can expect some good progress.
Sounds very interesting also. So energy is definitely a very important topic. So I will thank you once again, our speaker. Thank you, Professor Novoselov. Thank you, Nikita, for giving us an overview of the platform. And I thank all the audience to stay with us. I've seen that we have been having people joining from many different places, and they were very active on the chat. So thank you again, and we'll see you maybe in the next series.